A vector space is a set equipped with an addition operation and a scalar multiplication operation obeying a whole bunch of axioms. So if you just have two vector spaces and an arbitrary function between their underlying sets, that won't tell you anything about their relationship as vector spaces because it doesn't necessarily take into account the addition and scalar multiplication operations. That means when we study maps between vector spaces, we should be interested in the maps which somehow respect their vector space structure. In other words, which behave nicely in some sense with respect to their additions and scalar multiplications. Those maps are called linear maps. Here's the definition of a linear map. If you have V and W which are vector spaces over the same field F, that's important, then a function t from V to W is called a linear map if it obeys the following two properties. The first property says that for all scalars L and for all vectors V, we have t of LV is the same as L times t of V. That property has a name. It's called respecting scalar multiplication. The second part of the definition says that for any two vectors V and W, it must be the case that t of V plus W is equal to t of V plus t of W. Again, this property has a name, and what it is it's called t respecting vector addition, or just addition. The property of linearity is so common that it has several different names. So sometimes people will say T is a linear map between two vector spaces. They may even say T is a linear function between two vector spaces. They may say T is a linear transformation, or they may say T is linear. All of those mean the exact same thing. Namely, they mean that T is a function between two vector spaces satisfying properties 1 and 2 from the definition which we've written at the top of the slide there. Let's immediately look at a non-trivial example of linear maps because you're actually familiar with lots of examples of linear maps. So the first and perhaps the most important example of a linear map is that multiplication of vectors by matrices defines a linear map. I'm going to introduce some notation which is standard and which we'll use again and again. So let's let A be an m by n matrix whose entries come from a field F. We're now going to define a function t sub A, which will be a function from F to the n, so height n column vectors with entries from the field F, to F to the m. And we define it by t sub A of a vector x is the matrix multiplication A times x. If you do that, TA is a linear map. The reason is that the two properties in the definition of linearity simply translate into familiar properties of matrix multiplication. So if we have a scalar L and a vector x, then TA of Lx is by definition A multiplied into the column vector Lx. And you know that one of the properties of matrix multiplication is that A multiplied into Lx is always the same as L times Ax. Similarly, property 2 holds as well, because if you look at TA of a sum of two column vectors, that's A multiplied into x plus y, so actually let me just go back there and rewrite this as TA, L times TA of x. So you can see this really did obey property 1. Back to property 2 here, TA of x plus y, that's A times x plus y, and one of the properties of matrix multiplication is that it distributes over addition. So this is AX plus AY, which is TA of x plus TA of y. Again, that's just a standard property of matrix multiplication, that it distributes over addition, and therefore our maps TA satisfy both properties in the definition of a linearity, so they are linear maps. And this notation of TA, we're going to use that all the time. That's standard notation throughout the rest of the course. Let's look at some more examples of linear maps which are already familiar to you. First of all, we're going to look at two standard linear maps which exist for any vector space V. There is an identity map from V to V. Which is just the do-nothing map, so the identity applied to a vector v is just that vector v again. And there's also a zero map, which I'll in general just write as 0 from v to v, given by the zero map applied to any vector v is just the zero vector in capital V, and both of those things are linear. So you can check the two properties of the linearity definition very easily. Those two maps are always linear maps. Okay, let's look at an example of a map which is not linear. So we will take S, which is going to be a function from the set of n by n matrices over a field F to the set of n by n matrices over a field F. We're going to define that by S of the matrix A is A squared. Then this is not linear. At least not in general. In general, it won't obey either of the linearity conditions. So for example, S of lambda A, for a scalar lambda, that is lambda A squared, so that's lambda squared A squared. And in general, if you're able to find a scalar lambda which is not equal to lambda squared, well then this is not, in general, lambda times S of A. When I say in general, I mean that it doesn't hold for all scalars lambda and all matrices A. But in order to respect scalar multiplication, you've got to have property 1 from the previous slide for all scalars lambda and all elements of the vector space A. So it doesn't obey the first property, and it doesn't obey the second either, because S of A plus B, well, that is A plus B squared, and you can expand this and you'll get A squared plus AB plus BA plus B squared, and in general, again, it's not equal to S of A plus S of B. There's certainly a term there equal to S of A and a term there equal to S of B, but in general, AB plus BA won't be the zero matrix. So for linearity, it has to be true for all A and B that S of A plus B is equal to S of A plus S of B, but that won't be true always. So this is not going to be a linear map. Let's now look at an example of something which is a linear map again. So we're going to define D, which is going to be a function from R of x to R of x. You will remember R of x means the set of all polynomials in one variable x. And we're going to define D of a polynomial f to be its derivative df by dx. And this is a linear map. So D is a linear map. And the reason for that is because the two linearity properties are just familiar properties of differentiation. You know for all functions, not just polynomials, that the derivative of f plus g is always equal to df by dx plus dg by dx, which for us is d of f plus d of g. So that means our differentiation map D on the set of all polynomials certainly obeys the second linearity condition, and it also obeys the first linearity condition, because if you look at D at a scalar multiple of f, well, that's d by dx of lambda f. And again, a familiar differentiation rule tells you that a derivative of a multiple of a function is just that multiple of the derivative of the function. So the fact that d of lambda f is equal to lambda times d of f for any real number lambda is just a standard differentiation rule. And so this differentiation map obeys both of the properties in the linearity definition, and therefore it's a linear map. Finally, let's look at one more example. We're going to define a function t from r squared to r squared by t of a column vector xy. I think my codomain is actually going to be r cubed, and I'm going to define this to be 2x plus y, 0, y minus x. So I'm going to ask you the question, is T linear? Okay, you should try and check this. So you have two properties that you need to check. So you need to work out T of, let's take two vectors, x, y, and z, w. Oh, this is property 2, isn't it? So actually, let's do them backwards. T of x, y plus z, w. Well, that is T of x plus z, y plus w. And you can work that out. And you need to know, is this equal to T of xy, which you can get from the definition, plus T of zw. So you need to know, is it true that this thing and this thing are always equal to, no matter what x and y and z and w are they always equal? In property 1, T of lambda xy, well, you know how scalar multiplication works in R squared. That's lambda x, lambda y. So you can work that out. And you can also work out lambda times T of xy, because you know the definition of T of xy. So you can just scalar multiply the thing on the right by lambda and see what you get. And again, you've got to work out, is this thing always the same as this thing? So I'm actually going to pose one further question, which is, what if T of xy was defined to be slightly differently? So let's say we had the exact same thing, except we had a 1 in the middle instead of a 0. So is that linear? Again, you have to check exactly the same two things. You've got to check whether property 1 and property 2 in the definition of linearity hold, and I've just shown you what you need to compute in order to check that. I will tell you the answer at the start of the next lecture.